Hi everyone, can you hear me? Thanks, Peter. All right, welcome back everyone. So we've been going through this course quite slowly, but that's all right. It's required a lot of machinery to set up. But basically now we're ready to go through some of the more interesting scientific examples of exponential asymptotics. Now, one of these examples we had already reviewed in the very first lecture. This is the famous crystal growth problem. So the intention of today's lecture is to go through this nonlinear ODE example, which basically sets the stage for a lot of the techniques applied to more difficult problems. To resolve this issue, why was it that this nonlinear ODE seemed to exhibit, an appropriate asymptotic expansion, but actually there are no solutions that we found. And then to see the connection with exponential asymptotics. Okay, this material, there are lecture notes for these materials. It should be in one of the forthcoming chapters, but I've been a bit slow with generating them. But you should be able to see them soon online. Now, okay, so it's been a few weeks now, but the problem that we were looking at was this third order differential equation for this interface angle phi. So this was a geometric model of crystal growth. And I'll remind you in a minute what phi is. The situation that we're trying to model is this tip of a snowflake, for which if I take a point along the interface, S is the arc length parameter, so S is equal to minus infinity on the bottom and S is equal to positive infinity at the top. And phi is the angle that the interface makes, the normal of the interface makes, so this is the normal here, with the x-axis. And the way that you arrive at this kind of equation is you make the assumption that the velocity of your interface is moving, the normal velocity of the interface is moving as a function of the curvature. So the more highly curved the snowflake tip, the greater the velocity. And in order to ensure stability in the problem, right, so under this assumption of Vn proportional to curvature, in order to ensure stability, you need to introduce this epsilon. So the epsilon here is almost like a regularizing mechanism to make it makes sure that solutions don't blow up. And in the first lecture, we had demonstrated that under these assumptions of the boundary conditions tending to minus pi by 2 at the bottom here, and then phi tending to pi by 2 at the top here, it seems to be the case that you can develop asymptotic expansions to this problem at every order, epsilon squared, epsilon to the 4, and so forth. And these asymptotic expansions seem to satisfy the necessary boundary conditions to this problem. But weirdly enough, we showed you a numerical simulation of this problem starting from minus pi by 2. I just kind of solved this third order problem, moving towards s equal to positive infinity. And it didn't seem the case that it was possible to land at pi by 2 when you got to s is equal to positive infinity. And as you can imagine, the issue is related to exponential asymptotics. and these exponentially small terms that are actually beyond all orders of the asymptotic expansion, but are somehow crucial to invalidating that boundary condition at positive infinity. Okay. Now, before you get started on this problem, it might be worth re-examining the boundary conditions for this problem and to see why it is that you might be suspicious of whether or not this problem has a solution or not. So what you can do is you can deconstruct this boundary condition. So this is a third order problem, and it looks like you have two boundary conditions to this problem here, but what we're going to do is we're going to deconstruct what are these two boundary conditions equivalent to. And you can do that by basically just doing a linearization. So let's let phi be equal to minus pi by 2. We're going to look at the boundary condition at s equal to minus infinity. So let's let it equal to minus pi by 2 plus some function f of s. And let's make the assumption here that f is small. In that case, you can expand the cosine term here. So under that linearization, cosine of phi will then be cosine of minus pi by 2, which is 0, plus the first correction term here. So cosine of phi will just be basically f of s to leading order in f. And so that tells you that you have epsilon squared f triple prime plus f prime is equal to f, valid as s goes to infinity. So this should be rather twiddles if you want to keep it to this order of approximation as s goes to minus infinity. So this is the equation that should be valid far on the left at minus infinity. Well, this admits exponential solution, so if I just let f of s be basically a times e to the, say, m times s, I have to solve a cubic equation, epsilon squared times m cubed plus m twiddles 1. And I can do so. I can develop the asymptotic approximations to that problem. You can see one of the modes, one of the m's will be near 1, and the other two, you have to do a little bit of analysis to show what they are. But you can show that basically the three modes are either m twiddles 1 or m twiddles plus or minus I over epsilon minus a half. Okay, plus order epsilon corrections and so forth. Okay. So basically, at minus infinity, the solution has to behave like a linear combination of exponentials with these three modes, and you have that f of s should be, say, a1 e to the s plus a2 e to the minus 1/2 s times e to the I over epsilon times s plus a3 times e to the minus 1/2 times s times e to the minus I s over epsilon. Now at minus infinity, this one is perfectly fine. That's just exponential decay. But then these two modes can't be there in order for your solution to be bounded. So that tells you that a2 and a3 must necessarily be set to 0. So actually, this single boundary condition at minus pi by 2, if you think of it as the constraints on the coefficients here, is in fact equivalent to two boundary conditions at minus infinity. So then you can do the analogous study at positive infinity, and you'll come to the conclusion that in fact there are also two boundary conditions to the problem at positive infinity. In fact, this problem is translation invariant, so you can actually set the origin of that problem arbitrarily. So that gives you an additional degree of freedom. But you should really only have 3 for this problem which lends you to think that perhaps this epsilon is not actually a free parameter, that epsilon is constrained, and there is some evidence, because the problem is overdetermined, to think that this problem actually doesn't have a solution. So that's one way to kind of see that there is something a bit suspicious about this problem. Okay? But as we said before, if you're doing your asymptotics, you might not think about it that hard. You might do this analysis only afterwards. And we're going to be doing our merry asymptotics and just expanding things order by order. And essentially the punchline is that we want to develop the exponential asymptotics to this problem and show that there are these switchings, these exponentially small switchings, and it's the case that they always have to be present at one of the boundary conditions at positive infinity or minus infinity, and those exponential switchings will invalidate the necessary boundary condition. So that's our root. Okay. So the way that you do this problem is always as standard. You're just going to try to expand things into powers of epsilon, or in this case, epsilon squared is the small parameter. And then you're going to try to find singularities in the complex plane. And you have universal rules that will tell you how those singularities are associated with Stokes lines. Then you want to sketch the Stokes geometry, the Stokes line geometry, and figure out what those switchings will be. Okay? So you're going to expand phi is phi naught plus epsilon squared, phi 1 plus so forth. At leading order, you have to solve, so at order 1, you have to solve phi naught prime is equal to cosine of phi naught. At order epsilon squared, you'll have phi naught triple prime plus phi 1 prime. And it's useful for you to expand the cosine function as well. So if I expand cosine of phi naught plus epsilon squared phi 1 plus so forth, and expand that for epsilon small, I'm going to have cosine of phi naught minus epsilon squared phi 1 times sine of phi naught plus dot dot dot. So this is our first example. All the problems that we studied in the last few weeks were linear problems, right? The exponential integral, the complementary area function, and the area function. And the basically why linear problems are a lot easier from the asymptotic sense is that you don't have this kind of nonlinear nastiness, and you can very easily write down the order epsilon to the n equation, at least for most problems. You can easily write it down, even though you may not be able to solve it. Nonlinear problems have this kind of property where you have to work a lot harder at each order, but it turns out that this is not going to dissuade us from extending our exponential asymptotics. Okay? So we have phi 1 prime, and then I need the sine term on the right-hand side there, so that's a minus phi 1 times sine of phi naught. Okay, and you can see that this is always what happens. You have a linear operator on the phi 1 equal to something that depends on the minus phi naught triple prime. Okay, and so what we're going to have is there will be singularities in the complex plane for phi naught, and again, every subsequent order depends on derivatives of the previous, and there's a good chance that these derivatives will lead to divergence. In general, at order epsilon to the 2n, so again, this is a problem which is distinguished from linear problems, so you have to decide what terms to keep when you look at the order epsilon to the 2n equation, because obviously this is much more complicated. It now has a lot of cross terms from this cosine of phi. And the idea is that the terms that you have to keep should be terms which are of high derivatives and terms which have a high index in n. So it's a bit easier if I write that down firstly. So I'm going to have phi n prime. So this term will be at order epsilon to the 2n, of course, phi n prime. And I'm going to have phi n times sine of phi naught, which was the first term on the right-hand side here. This will be a phi n times sine of phi naught for the epsilon to 2n. I'm going to have the triple derivative of phi n minus 1, and then I'll have all the other stuff. So all this other stuff here was from the expansion of the cosine function. We only had to keep, in this case, the one of the terms that was proportional to phi n. But you should also have terms which will be things like phi n minus 1 times the derivatives as well. But for reasons that will be a bit more clear in a minute, you only need to keep the phi n term. Okay, so this term, this stuff here, these dots will be things like phi n minus 1 times the derivative of phi naught, phi 1, etc. Right, from expanding this cosine term. The reason why you only need to keep this phi n here is because of the divergence. So as n goes to infinity, this phi n will be much larger than phi n minus 1, which will be much larger than phi n minus 2, etc. So it turns out you only need this one here. You also need to keep any terms which have a high index n and have a derivative in them. Okay? And it will be the case, the algebra, when you do the algebra for these late orders, which we're going to be doing soon, it will be the case that, in essence, every time you take a prime, this is almost like shifting the index by +1. So you see that this phi n prime is then roughly, it's going to be the same order as this phi n minus 1 triple prime. It's not quite a shift of +1. And then this will be involved in the next order. Okay, so that was a little bit confusing, but you'll see quickly what the trick is. Okay? Right, so you have now a mechanism determining the order 1 problem, the phi naught problem, the phi 1 problem. The solution for phi naught, in this case, you can write it down in closed form. You have to integrate this function, and I think we wrote it down before. But it's the case that you don't actually need it in principle for more complicated problems, as long as you have a little bit of an insight about what it's doing in the complex plane. Okay? This problem here you can integrate, though I have to admit I haven't done it myself directly, but you can double check that this is the solution So minus pi by 2 plus 2 times arctan of e to the s. And if I substitute this into this, I'll get an identity. I can also verify that having written down this explicit solution for phi naught, if I take that in the limit of minus and positive infinity for s, I will satisfy the boundary condition. So this seems to be a legitimate leading order solution to the problem. If any of you manage to actually find this antiderivative directly from integration, you should let me know. I tried to finagle with it, but it's a bit harder than it seems. You have to do some trig substitution, I think, to get that there. Okay, so let's talk about the singularities of this problem now. So I can write the arctan function. So I can use the fact that arctan, or tan inverse of u, is I over 2 times the log of u plus I over u minus I. And so I'm interested in those locations where e to the s plus I or e to the s minus I is equal to 0, and then I can double check that those occur along the imaginary axis. So this will tell me that the singularities of phi naught occur at the odd multiples of pi by 2. So pi by 2, 3 pi by 2, 5 pi by 2, etc. And so they occur at if I just solve with u plus I and u minus I equal to 0, put an e to the s in there, I'll have that this occurs at the points, which I'm going to write, I'm going to index it with a k, s equal to sigma k in the complex plane, and they're 2k plus 1 pi times I over 2 for k. Okay, so if you didn't want to do it this way, you can basically just put this into a contour plot in MATLAB or Mathematica, put s to be complex numbers, generate the picture for yourself in the complex plane, and you'll notice the singularities at those locations. Okay. So let's erase this bit here. So this is, again, prototypical of our nonlinear problems. We have singularities, and previously for the area problem in the exponential integral, those singularities were only at singular points, only at one point, right? At the origin or plus or minus I or something. Here we have an infinite set of singularities up the imaginary axis. So this is the real part of S. This is the imaginary part of S. And they're up the imaginary axis at pi I over 2, at 3 pi I over 2, and then down the imaginary axis at multiples in the same fashion. Remember that when you're doing this, you do have the physical world to worry about, and in the physical world, your crystal is arranged in that way, ABC, and this lies along the real axis, ABC, here. So here we're talking about the non-physical complex plane, right? But so all the physics is happening along the real axis. So the kind of questions that we're wondering about is, what do the Stokes lines look like, and do they intersect the real axis? Because at that point you would expect a real valued exponential to appear, a real valued oscillation to appear. Okay? So this might be sigma 1, sigma 2, etc. And then this, I think the way I've indexed it is sigma 0 here, and then sigma minus 1, etc. Okay. So now every one of these singularities is going to lead to divergence. Well, that's not known a priori. It's just a guess, right? You're saying that it can be the fact that if phi1, if my leading order problem is singular at these points, in the fashion that I'm taking the derivatives with this process of every derivative making the singularity worse, it can be the fact that this is going to lead to divergence. Not all singularities in your leading order problem will lead to divergence, only ones of sufficient strength. Okay? And so your divergence is also very complicated, right? So you have a factorial over power type expression, but you really have one, you might think of having one for each of these singularities. And that will be the case, but it will be also the case that these singularities are then associated with exponentials, and the biggest exponentials will be associated with the closest singularities to the physical axis, to the real axis there. So the exponentials get smaller the further out the singularities are. So you don't have to worry about the infinite set going down. You only have to worry about the closest ones. Okay? All right, so the next step is for us to characterize the divergence as n goes to infinity, and this is where we use our intuition. Before I do that, I just want to write a little comment here. So I can double check that phi naught has logarithmic singularities. at s is equal to sigma k. And then I can go to one order higher and check what the singularities are in phi 1. And I can double check that phi 1 has the behavior of a constant times s minus sigma k to the minus 2 as s tends to sigma k. So you can see from this trend, at least just from these first two terms, that the singularities does seem to be getting worse as you go to higher order. It started off logarithmic, which is quite a weak singularity, and then it's getting worse. Okay. So now what you want to do is you want to posit what the trend is for the factorial over power. And in this case, you're going to have a factorial over power, but it's going to be a little bit different. It's actually a 2n plus gamma instead of an n plus gamma. Everything is a function of s. Gamma is constant, and q and chi are functions to be determined. And this 2n is basically because you'll see in a minute that the terms that determine the divergence are coupled 2 orders apart in derivatives instead of 1 order apart in derivatives. Okay, so now you go and write down your phi n equation again. So your order epsilon to the 2n equation is phi n prime. Let me write phi n minus 1 triple prime on the left-hand side there, plus phi n prime plus phi n times sine of phi naught is equal to dot dot dot. And remember, every time you take a derivative of this factorial over power expression, it's going to get bigger because this n plus gamma is going to be moved to the top. This is 2n plus gamma on the bottom there instead of n plus gamma. This 2n plus gamma will be moved to the top, and that enhances the divergence of your factorial expressions. You can also see that because of the 2n here, you kind of have to do it twice to get an effective shift of n to n plus 1. Okay, so do we want to do that? Sure, let's just do the leading order expressions rather than the next order as an n. So you can see that if I take phi n prime here, I'm going to have a minus chi prime. I'll have a 2n plus gamma times a gamma function of 2n plus gamma times a q over chi to the 2n plus gamma plus 1. And you can see this one here is equivalent to gamma function of 2n plus gamma plus 1. And then you take the second derivative and the third derivative. And so the second derivative prime will be minus chi prime squared. This will be a plus dot dot dot. We're just going to keep the leading term here and ignore all the other ones. This will be a gamma function of 2n plus gamma plus 2 over chi to the 2n plus gamma plus 2. And then if I take a third derivative, I have a minus chi prime cubed. And I think my signs here should be swapped. That should be a positive sign. That should be a negative sign here. This is gamma function of 2n plus gamma plus 3 over chi to the 2n plus gamma plus 3. And then you can see that if I then substitute in an index of minus 1 here, this will then be 2n minus 2 plus gamma plus 3, so it will be 2n plus gamma plus 1. And then that will match the index for this phi n prime, which will be from this, this is a double prime, which will be from here. Okay, so if you just look at these two terms here, you'll see that the leading order should be minus chi prime cubed plus chi prime from here, it's a minus chi prime, I think, is equal to 0. It'll be multiplied by the q's, which will be the same between the two terms. I'm missing a q here, missing a q here. And then it's going to have the same denominator of chi on the bottom there. You see? So it's actually, once you understand how the indexing works, it's not too hard to figure out this equation here. You have to do a little bit more work to get the equation for q, but you're going to have to go to one extra order there. And then you can also see why I said to you that you only need the phi n term here from the expansion of the cosine, which happened on the right-hand side, because this phi n will be brought in at the next order in n. It's going to involve figuring out what all the other next order contributions are from these two terms here, but you won't need the next phi n minus 1. So at this point, you would conclude that either chi prime is equal to a constant, which is not that helpful because you need a chi which is singular at the points of the singularity. You need a chi which is 0 at the points of singularity. Or it's the case that chi prime, it looks like chi prime squared plus 1 is equal to 0, and hence chi prime is equal to plus or minus I. Okay? So now this function there needs to be 0 at the singularities. So that tells you that the possible form of this divergence is chi is plus or minus I times s minus sigma k for the different k's. Okay, so each singularity in the complex plane here is producing a divergence which is a factorial over this function to the power of 2n plus gamma. And you can think of the general divergence, if you like. Let me erase this stuff here. You can think of the general divergence as a sum over all the k's here. And each chi k here is plus or minus I times s minus sigma k. That's a general ansatz, but because of the kind of linearity of the process, you can just work with a single term. You just have to work with the single 2n plus gamma. Okay? And then again, because of reasons that's going to be a bit more clear, we're only going to have to focus on the nearest singularities to the physical free surface, because then those are associated with the largest divergences and also the largest exponentials. Okay? Right, so having found the chi now, you understand the general process. To get this q, you have to go to one order higher in n, and you can also find that q, again, this is a simple enough problem that you can solve for it, but it's essentially a constant of integration times the root of a cosh of s. Okay, and this is constant to be determined. Right, so at this stage in the game, we've determined the q, the chi, and it remains determined the gamma, the power here, and also this constant of integration, or this constant, this prefactor. And as expected, this is always the most difficult step, is to determine that constant. You can also just kind of do it at the very end there and just hope that you're not going to really need it. And as long as that constant is non-zero, you're going to be able to get your conclusions. Okay, so that's basically it. Now, to figure out the gamma and the lambda, you're going to have to do some inner singularity matching. You're going to have to take your ODE problem, zoom in into a little bubble around the relevant singularities, and then find the right gamma and the right lambda that allows you to match inner and outer solutions. Okay. So now so let me write down the expression for phi again. So this is basically q of s times the gamma function of 2n plus gamma over chi to the 2n plus gamma. And we found that q was lambda times the root of cosh, and chi was plus or minus I times s minus sigma k. Okay, now at this point in time, you kind of know by your universal rules, or rather I'm just going to tell you and you can double check, that the exponential that gets switched on, if I write that as phi exp, is essentially going to be 2 pi I over epsilon to the gamma times q of s e to the minus chi of s over epsilon. And you know this in a variety of different ways. You know it because I've told you to be as such, that it's going to be turned out to be that fact. You could check it by doing Stokes smoothing and truncating your asymptotic expansion, substituting it into the differential equation, finding the right truncation parameter, and then rescaling around the Stokes lines and integrating. Or you can also do it in the fashion that we showed in the last lecture, which is that you could almost do Borel summation. You can write down a divergent series, write down the expression for the gamma function in the limit that n tends to infinity, do a little bit of magic with swapping, integration, and summation, and you would come out with this universality. So again, and in this case, this is a 2 gamma and I think a 2 epsilon. I should double check this case, but because the scaling for this problem was a bit different. You have an epsilon squared instead of an epsilon. And I should double check this for you. I actually think it is the same as gamma and epsilon here. I'll have to double check that in the notes. But basically, this is one universality that once you found your q and your chi, there is this expression for the exponentials that's switched on. And the other universality is that the Stokes lines are given where the real part of chi is positive. So the Stokes lines will be where the real part of chi is positive and the imaginary part of chi is equal to 0. So for the case of, if I just look at sigma 1, which is pi I over 2, then for this singularity, there are 2 singulants. There are 2 chi's associated to it, one with a plus I and one with a minus I. But you see it's the case that if I take chi to the plus I of s minus pi I over 2, that the location where the real part of chi is positive will be along the imaginary axis, when this is purely imaginary, and when it's basically equal to minus I times t. Right? So if this quantity, if s minus pi I over 2 is equal to minus I times t, I times I minus 1 times a negative, then this quantity will be real and positive. Okay? So in other words, if I look at that singularity at pi I over 2, and I take this chi, the one with the positive I, then along the imaginary axis going downwards, this condition is satisfied, and you would expect then that along this line, that's a Stokes line. So that as you go in the complex plane and you cross this line, you're going to switch on this exponential with this chi. You would come to the same conclusion for the other singularity. So if I looked at phi 2, I shouldn't have indexed it by k, but I think this is phi 0, so I'm going to call it a phi plus and a phi minus. If I look at phi minus is minus pi by I by 2, then it's the case that if I take chi minus, this is now s plus pi I by 2, and I examine this chi, then it's real and positive going upwards. Okay. You'll also notice the fact that you began life talking about real valued functions, right? This is a real differential equation with real boundary conditions. So of course you would expect your solution to be real along the physical axis. The exponentials that you switch on are intrinsically complex valued, right? They have things like I here and I here. But it's the case that if you were to switch on from one exponential and switch on from the other exponential and you add the two, then they would add up to be real valued along the domain. So that makes sense for there to be two complex conjugate contributions. Okay. Now, you're going to have Stokes lines from each of the singularities up the axis, and those will also generate exponentials, but those will be smaller in magnitude. Now, how do you see that they're going to be smaller in magnitude? Well, the most expedient way is to notice, to look at this expression here, and essentially this chi along the axis, it will have a real valued component and it will have an imaginary component. Now notice along the axis, as you move along in S here, I mean, you can, sorry, I just realized, so you can of course just substitute this directly into there. This I times, you'll have a component which is I times S over epsilon, and you'll have a component which is minus I times S over epsilon, so that will be oscillatory along the axis. And then you also have a component which is I times minus I, so that's a positive one, will be pi by 2 from this exponential, positive pi by 2, real valued pi by 2. And so that tells you that the exponential associated with this chi plus will be exponentially small with magnitude e to the pi by 2 minus pi by 2 over epsilon. Okay? And then you can also see that the other exponentials which are generated from points up higher along the imaginary axis will be associated with a larger value here, 3 pi I over 2 and so forth and so on. And actually when you multiply them out and you put them in the exponential, they're associated with a larger exponential decay. And so that's why all the subsequent singularities up the axis will be exponentially dominated by the nearest ones, and why we only consider the nearest ones. Okay, let me write that out properly, I suppose. So you would expect that your exponential if I just add the two most immediate contributions, I would have 2 pi I over epsilon to the gamma. I'm going to assume that the gammas for both are actually the same, but I'm going to explain that in a second. I'm going to have a lambda 1 here times a e to the minus chi. So if I think of chi plus being I times s minus sigma k, which is I times s plus pi over 2. This is from the singularity in the upper half plane. Then I'm going to have an e to the minus pi over 2 epsilon. There's my exponential smallness. And then an oscillation, e to the is over epsilon. And I'm missing my cosh of s factor, which is coming from the big Q here. Okay. I'm then going to add this to the exponential, which is generated from the singularity in the lower half plane. But the claim here is that this has to be the complex conjugate of whatever I wrote in here. And the reason why it has to be a complex conjugate is it is by symmetry. I know my solution is real valued along the axis here. So anything that I switch on from the upper singularity has to add together with whatever switched on from the lower singularity in order to produce a real valued function along the real axis. So this, without even going and doing the computation for the sigma that corresponds to minus pi by 2, you can expect it to be the complex conjugate. Okay, so you can kind of see that this will basically going to produce some number over epsilon to the gamma times cosh of s times e to the pi I, e to the minus pi over 2 epsilon times a cosine or a sine of s over epsilon plus a phase shift, if you rewrite things in the proper way. So this is purely along the axis. It is complex valued in the rest of the complex plane, but along the axis it boils down to a real exponential. You can also see that this thing here will invalidate the boundary conditions as s goes to infinity. This should really tend to 0 as s goes to infinity, and it doesn't do so. It's not only does it have this exponentially decaying component to it, which does tend to 0, but actually this cosh of s is screwing everything up because this is exponentially growing as s goes to infinity. And so that's why, if you remember the picture that we had presented of the numerics, the waves, you switch on a wave as you go from across the origin from minus infinity to positive infinity, and on this side here, it's actually getting larger. So this is always the example that we talk about, or it's a simple example that exponential smallness is not negligible, right? This is exponentially small when it's being switched on. It's negligible compared to your base asymptotic expansion, which is giving you that needle nose shape for your crystal. But by the time you get to infinity, it's actually substantial, and it screws everything up. Okay, now I want to just finish up by commenting on the gamma and the lambda. And when you get the notes for this, I'm missing an S here. Sorry, I wasn't missing an S here. This was the constant shift in the chi function, so there is no S here. So it's actually worse than what I said. I said that you do have something that's exponentially decaying as you go towards the right, because I thought there was an S here. It's actually exponentially small just purely in magnitude without changing the shape. But then this cosh function is providing you with an envelope. So you have some kind of envelope, and then your exponentially small oscillations, quote unquote exponentially small oscillations, because it's not exponentially small at positive infinity. Okay, so what are some comments to make about at this stage? Well, so firstly, let's just comment upon the remaining constants, gamma and lambda, right? So, so to determine gamma and lambda, so firstly, gamma is easy to get. Gamma is usually easy to get in most problems. and lambda is a lot harder. And you can see now why I said that it is often the case that you might not be purely interested in the lambda, because as long as it's non-zero. And in this case, that was the situation. The other thing that I want to just note here before I go on is that, as we said, the waves that you switch on, right, across these Stokes lines are of this form here, 2 epsilon times a, okay, I'll write them in the real valued way. The waves that you switch on are of this form. And so if you didn't know how to do the exponential asymptotics, you could attempt to do this numerically. You can solve your differential equation numerically, okay? And you would see, a solution profile which does something like this. So this is minus pi by 2, and it does not tend to a constant pi by 2 on the right, but it oscillates. But you could attempt to measure the oscillations, measure their amplitude, and measure their wavelength, and then verify these predictions. So you should be able to verify that the wavelength is 2 pi times epsilon in size, and you should be able to verify that the amplitude is scaling like this. You do these experiments with smaller and smaller epsilon and make this prediction. Generally, in your computations, verifying the wavelength and verifying the exponentially small nature is possible. You can solve these differential equations to good enough accuracy that you can double check these things. So even if you couldn't figure out that it was a minus pi by 2, you can get a number and then try to match the decay numerically. On the other hand, finding this gamma is a little bit harder because it's always being dominated by the exponential decay, but in some cases it is doable. You can generate numerical results over different epsilons, try to factor out the leading exponential, and then try to determine whether or not your prediction for gamma is correct or not. But as you can imagine, checking the lambda numerically is incredibly difficult, right? Even for this problem where it's essentially a fairly simple nonlinear differential equation, in order to detect this lambda, you would have to strip out first the exponential behavior, then strip out the algebraic behavior, and see if you can determine from your numerics whether the lambda is correct or not. So this is often a trend for these exponential asymptotics problems, that lambda is the longest procedure to follow to obtain the value of lambda. It's also incredibly hard to check whether or not your procedure has given you the right result, because numerically verifying these laws can be very difficult. Now, as we said before, to figure out gamma is the shift that you need in order for your late term ansatz to match the singularity that was generated at the early terms. So you'll remember that I said to you that phi 1 is actually of order s minus sigma k to the minus 2, right? And you'll remember that chi was basically is essentially of order s minus sigma k. It's I times s minus sigma k. So if I assume that this rule is true, then the divergence must follow in the limit as I approach the singularity. That rule tells me that phi n is of order, well, what do we have? We have q of s, which behaves, that's a good question. What does q of s behave like? It's cosh of, yeah, okay. So I need the behavior Q of S as well as you approach each of these points, and then you can double check that Q of S is of order root cosh of S, and then you have to go and figure out what is the cosh function doing as you approach these multiples of pi I over 2, and you'll find out that it's basically of order S minus sigma to the 1/2. So you put all of these together, and that tells you that you have S minus sigma to the 1/2 from the Q, and then you have S minus sigma to the 2n plus gamma from the chi, and at n is equal to 1, if I want to match this fella here, I basically need 1/2 minus 2 times 1 plus gamma to be equal to minus 2. Right? So what does that give me? 1/2 plus 2, which is 5 on 2. 5 on 2 is 2 plus gamma. And so gamma 2 is what? 4. Gamma is 1/2. Okay, so there's our back of the envelope calculation of what gamma has to be. Gamma is such that the power of your late orders behavior is going to match one of the powers of the terms that generate the singularity. Okay. Now from this, you can also get the fact of how to do the inner analysis, or at least how to get started doing the inner analysis, and it's a real pain to do so. But the inner region, the criteria we gave for the inner region is that it's the size near the singularity where all your later terms of the asymptotic expansion become the same order. So the inner region, for instance, is where epsilon times phi 1 is order epsilon squared times phi 2, etc., which is of order 1. And you can verify that this is basically where this is epsilon squared because everything's going up in powers of 2. This is epsilon to the 4. And you can verify that this is basically where S minus sigma k is of order epsilon. So near each of these singularities, there's a little neighborhood of order epsilon that you need to do the analysis in. Then you need to do a coordinate transformation where you're going to set S minus sigma k is epsilon times a new inner variable. And you have to go through the kind of scaling and rescaling and transformation of the differential equations, and you can refer to the notes for the full details. Okay, so we basically, so what's the punchline? The crystal growth problem has no solution. Now we didn't prove it, we proved it in the limit of epsilon tending to 0. So I think at this stage what you can say definitively is that if epsilon is small, right, then asymptotically you cannot satisfy the far field conditions in that problem, and there is no solution in the limit to epsilon tends to 0. I suppose this doesn't tell you that there is never a solution for all values of epsilon. So there might be epsilon large theory or epsilon order 1 theory where there might be a solution that does satisfy the boundary conditions, but also your numerics tell you that this is quite unlikely, and also our counting argument with the boundary conditions told us that this was a little bit unlikely as well. So if you're doing the geometric model for crystal growth, what would you conclude? Well, you'd conclude that there is something wrong with your model. It does not seem to admit the solution that you would have thought. It's also quite funny because this is a problem where every asymptotic, your basic asymptotic expansion does seem to give you something that's physically realistic. Now, I want to end with 2 comments. So the first comment is that if you were to interpret the solution in our exponential asymptotics in the way that we've done it here, then our exponential asymptotics are saying that if you were to move along from s equal to minus infinity, as you cross s is equal to 0 here, you're necessarily switching on this exponential. And this exponential is happening, this switching on is happening somewhere in the complex plane, so you can't really plot it, but you can kind of think of it as a singularity which is associated with the nose of the crystal, right? If I think of it in the complex plane. And across this point, I'm going to switch on this oscillation. And it doesn't satisfy the correct boundary conditions, but then actually if you look at the experimental pictures of snowflake crystals, they seem to exhibit an oscillation on the far end. And I think at the time, after we realized that the crystal growth, this geometric model for crystal growth does not actually admit solutions, it does inspire the question of whether or not there is something real in the way that you have derived these oscillations, that they do exist in nature in some fashion. Now, this analysis was done by Kruskel and Seeger. So they are the original exponential asymptotics are associated with Kruskel and Seeger in 91. And in that paper, which is actually a really nice paper, I think published in the Studies of Applied Maths, they also present a modification of the crystal growth problem where you can have solutions. And the modification is by thinking of the third order problem with the usual cosine of phi on the right hand side, but if you assume anisotropy, right? So if you assume that the growth of the interface is not happening equally in all directions, then you can produce this kind of model instead, where this alpha is your anisotropic parameter. In the limit that alpha tends to 0, you recover the original problem, and alpha is between 0 and 1. Okay? And so then the question is, now this problem does admit solutions. And so just by introducing this denominator with 1 plus alpha cosine of 4 phi, it will admit solutions. And it turns out that if you do the Stokes line structure for this problem, it's going to be almost the same as the one that we just did. In fact, if you remember, the chi function that we found did not care about this term on the right-hand side. It only cared about these two terms. So if you were to repeat the analysis for this function, you'd find that the chi is still linear. It's still I times s minus singularities. So in order for this problem to admit solutions, there has to be something different about the singularities in the complex plane. Right, and then in the next lecture, I'm going to show you what's different about this problem. We're not going to spend too much time on this problem, but I'll show you how it's different, how it is that this problem, just by making this modification, can now admit solutions, and then we're going to go on to another physics-inspired problem of exponential asymptotics. All right, thanks everyone.